Beneath the dark blue waters, invisible forces are at work. Massive oceanic plates slowly collide. They are reshaping the very foundation of our world. Deep beneath the ocean's surface, massive oceanic plates slowly converge, reshaping the very foundation of our world.
Before we begin tonight, I want you to imagine something with me. Not something abstract, something specific. Imagine you are floating in the middle of the Pacific Ocean. No land in sight, just water in every direction, as far as you can see. Now imagine you could somehow see through the water below you, down through the surface, down through the sunlit zone, the top 200 meters where light still penetrates, down through the twilight zone where the light fades from blue to black, down through the midnight zone, total darkness, crushing pressure, cold beyond cold, down through the abyssal plain, the vast, flat, sediment-covered floor of the deep ocean, 4 kilometers below you, and then down further still, through the lip of something, down into a slot in the ocean floor, down and down and down, until you are 11 kilometers below the surface. A leva that's not a metaphor, that's not an exaggeration. The deepest point in the Mariana Trench, the Challenger Deep, is 10,935 meters below the surface of the Pacific Ocean. To put that into terms your body can feel, Mount Everest, the tallest mountain above sea level, is 8,849 meters high. If you placed Everest at the bottom of the Mariana Trench, the summit would still be more than 2 kilometers underwater. And almost nobody has been there. But first, tell me where you are tonight. What country, what city, what time? I love knowing where these quiet, curious, late-night listeners are gathering from. Drop it in the comments before you fall asleep. Now, let's go down. Opening cinematic. There is no light here, not dimness, not the blue dark of twilight water, not even the faint bioluminescent glow that haunts the midnight zone. Here, at 11 kilometers, there is nothing. A darkness so complete, so total, so ancient that it has never been interrupted, not once, in 50 million years. The pressure is 1,086 times the pressure at the sea surface, more than 1,000 times. In practical terms, every square centimeter of any surface at this depth bears a weight of approximately 1,100 kilograms. The weight of a small car, pressed on every square centimeter of everything. The temperature is just above freezing, about 2 degrees Celsius. The same temperature it has been for millions of years. Stable, cold, patient. The sediment on the floor is soft, pale, composed of the remains of tiny organisms, foraminifera, radiolaria, that fell from the surface ocean over millions of years, millimeter by millimeter, building up a slow, soft snow of the dead that has been falling in this darkness for as long as the trench has existed. And in this sediment, in this cold and this dark and this pressure, things are alive. Not just bacteria, not just microscopic organisms that barely qualify as life by any human intuition. Actual animals with eyes, some of them with legs, some of them with mouths and stomachs and the basic machinery of living, in conditions that should make living impossible, in a world that nothing in human experience has prepared us to imagine. This is the Mariana Trench, the deepest place on Earth, and tonight we're going there, the deepest place on Earth. What the numbers mean, let me start with the numbers, because the numbers are the beginning of understanding, and because the numbers when you really sit with them, are astonishing. The Mariana Trench is located in the western Pacific Ocean, east of the Mariana Islands. Hence the name. The Mariana Islands themselves are named for Mariana of Austria, Queen Consort of Spain in the 17th century. The islands were given her name by Spanish missionaries. The trench carries her name too, by extension, though she never knew it existed and would have had no way of knowing, since the trench would not be discovered in any meaningful sense until 1875, when HMS Challenger, on its famous oceanic survey expedition, sounded the depth at a location near the trench, getting a reading of 8,184 meters. The first hint that something extraordinary was down there. The trench runs in a crescent shape for approximately 2,550 kilometers. A long curved arc in the Pacific floor, roughly 69 kilometers wide on average, but much narrower in places and much deeper in one specific place, the Challenger Deep, the lowest known point, at the southern end of the trench, measured with increasing precision over decades. The most recent, most careful measurements give a depth of 10,935 meters, plus au minus 8 mètres, 2,935 mètres. Let me make that real. A standard commercial aircraft cruises at about 10,700 meters altitude. The Challenger Deep is deeper than a commercial aircraft flies high. If you were on a plane looking down and the ground was at the level of the Challenger Deep, the sea surface above you would still be higher than you are. The trench is deeper than airliners fly. Or think of it this way. The tallest building in the world, the Burj Khalifa in Dubai, is 828 meters tall. You would need to stack 13 Burj Khalifas on top of each other to reach from the bottom of the Challenger Deep to the surface of the ocean. 13 of the world's tallest buildings stacked, and you'd still be underwater. The volume of the trench is also extraordinary. The total volume of the Mariana Trench has been estimated at approximately 6.4 million cubic kilometers. For comparison, Lake Superior, the largest of the Great Lakes, one of the largest freshwater lakes in the world, has a volume of about 12,000 cubic kilometers. The Mariana Trench could contain Lake Superior roughly 533 times. These numbers are not presented to impress. They are presented to establish something, the scale of what we're talking about, because everything that follows, the creatures, the geology, the chemistry, the physics, only makes sense against the background of this scale. This unimaginable depth, this extreme volume, this specific, extraordinary piece of the earth. The shape of the trench, the Mariana Trench, is not a simple slot, not a neat, vertical walled canyon. It is complex. Its cross-section varies enormously along its length. In some places, the walls are steep. In others, they slope gradually. The floor is not flat. It has ridges, knolls, depressions within depressions. The Challenger Deep itself has three distinct basins: the Western Pool, the Central Pool, and the Eastern Pool. Each one slightly different in depth, each one slightly different in character. The walls of the trench in the steeper sections rise at angles of 40 to 45 degrees. Not vertical, but steep. The slope is punctuated by ledges, by overhangs, by boulder fields, by the constant slow movement of sediment down the walls. Toward the floor, a slow, cold, dark avalanche. That has been happening since the trench was formed, how the Mariana Trench was born, the violence that created stillness. To understand the Mariana Trench, you need to understand plate tectonics. Specifically, you need to understand one particular tectonic process: subduction. The Earth's crust is divided into tectonic plates, roughly a dozen major plates, and many minor ones. These plates move continuously, driven by the convection of the mantle beneath them, the slow, hot churning of the rock below that drives the plates above, like objects on a conveyor belt. When two plates collide, what happens depends on what the plates are made of. Continental crust, the rock that makes up the landmasses, is relatively thick, about 30 to 50 kilometers thick on average, and relatively buoyant, made of lighter rock, granitic in composition. Oceanic crust, the rock that makes up the ocean floor, is thinner, only 5 to 10 kilometers thick, and denser, made of heavier rock, basaltic in composition. When oceanic crust collides with continental crust, or with older, denser oceanic crust, the denser material subducts. It is forced downward, beneath the lighter material, down into the mantle. This is subduction, the process by which oceanic crust is recycled back into the mantle, melted, and eventually returned to the surface through volcanic activity, a slow, violent geological recycling. The Mariana Trench was formed by subduction. The Pacific Plate, the largest tectonic plate on Earth, covering approximately 103 million square kilometers, is moving westward at a rate of 5 to 10 centimeters per year. In the Western Pacific, the Pacific Plate is colliding with the Mariana Plate, a smaller plate, the subduction zone where the Pacific Plate dives beneath the Mariana Plate, is the Mariana Trench. The trench marks the point of descent. The Hinge, where the Pacific Plate bends downward and begins its journey into the mantle. The bending of the plate creates the trench. As the Pacific Plate flexes, as it begins its downward arc, the leading edge of the bending creates a depression in the ocean floor. The trench, the deepest place on Earth, is the mark left by a plate that is bending, that is beginning to descend into the interior of the planet. The age of the trench, the Mariana Trench, is old, but not ancient by geological standards. It formed approximately 50 to 55 million years ago in the Eocene epoch, when the Pacific Plate began its current subduction trajectory, 50 million years. At that time, the dinosaurs had been extinct for about 16 million years. Mammals were diversifying rapidly. The continents were approaching their current positions, but still significantly different. India was still drifting north toward Asia. The Himalayas were not yet risen. Antarctica was beginning to cool. The world was warm and strange. And in the Western Pacific, the greatest geological feature of the modern ocean was beginning to form. At the rate the Pacific Plate subducts, about 5 to 10 centimeters per year, over 50 million years, the leading edge of the plate has descended approximately 2,500 to 5,000 kilometers into the mantle. The rock that was once part of the Pacific Ocean floor is now deep in the earth, slowly being reabsorbed, melted, remade. The trench is literally consuming the floor of the Pacific Ocean, the Mariana Islands. The Mariana Trench is not the only feature created by this subduction. The subduction also produces the Mariana Islands, the volcanic arc that runs parallel to the trench. about 200 kilometers to the west. As the Pacific plate descends into the mantle, it carries water with it, waterlocked in the minerals of the oceanic crust. At depth, under pressure and heat, this water is released into the hot mantle rock above the descending plate. Water lowers the melting point of rock. The addition of water to the mantle wedge above the subducting plate causes the rock to melt, producing magma, which rises through the overlying plate and erupts at the surface, creating the volcanic arc, the Mariana Islands, and further north, the Izu Islands, the Bonin Islands, all products of the same subduction, all built from the material of the Pacific plate, melted and returned to the surface in a different form. The geography of the abyss, what the trench actually looks like. Describing the geography of the Mariana Trench is challenging because we don't have a complete picture, not a high-resolution picture. The ocean floor mapping problem is one of the great ironies of modern science. We have mapped the surface of Mars at a resolution of approximately 25 centimeters per pixel. We have detailed topographic maps of the Moon, of Mercury, of asteroids that pass through the inner solar system. We have mapped the surface of Titan, Saturn's largest moon, through the clouds. But the ocean floor of Earth, we have mapped only about 24% of the global ocean floor at high resolution. 76% remains poorly known, mapped only with relatively coarse satellite-based gravity measurements that can identify large features, but miss the details, the valleys and ridges and seamounts and canyons of the ocean floor that make it as complex and varied as the landscape above water. The Mariana Trench specifically has been surveyed at relatively high resolution by a series of expeditions using multi-beam sonar, sound pulses sent down from ships, reflected off the ocean floor, timing the return to measure depth at thousands of points simultaneously, building up a picture, but even this picture is incomplete. The trench is so deep and the water column above it so long that sound pulses spread and weaken significantly before reaching the bottom, and the resolution of the resulting maps is still limited, much lower than what we can achieve in shallower water. What we know, the trench runs in a crescent, oriented roughly north-northeast to south-southwest. The Challenger, deep at the southern end, the deepest measured point, the floor of the trench varies in width. In some places, the flat bottom is only a few kilometers wide. In others, it broadens to 10 or 15 kilometers. The floor sediment is thick in places. Years of accumulated material washed down the walls and settled on the bottom. The walls rise steeply to either side. To the east, the Pacific Plate side, the wall rises to the general level of the deep Pacific Ocean floor, about 5 to 6 kilometers above the trench floor. To the west, the Mariana Plate side, the wall is lower, and beyond it lies the Mariana Arc, the chain of islands and submarine volcanoes created by the same subduction that formed the trench. The Challenger Deep specifically, the deepest part of the trench, has been visited by submersibles on several occasions and surveyed by autonomous vehicles. The floor here is covered in a soft, pale sediment, sometimes described as liquid by those who have disturbed it, because it is so fine, so loosely packed. That disturbance creates clouds of suspended material that take a very long time to settle. The sediment is dominated by the skeletal remains of foraminifera, single-celled organisms that live in the surface ocean. and whose shells rain down, when they die, year after year, for millions of years, building the sediment layer, centimetre by centimetre. The Hadal trenches in general. The Mariana Trench is the deepest, but it is not the only Hadal trench. Hadal refers to the ocean zone below 6,000 meters. The term comes from Hades, the underworld of Greek mythology, and it is apt. There are approximately 37 Hadal trenches in the world, all located in subduction zones, where one tectonic plate dives beneath another, creating the characteristic V-shaped slot in the ocean floor. The Tonga Trench, northeast of New Zealand, second deepest, reaching about 10,800 meters. The Philippine Trench, reaching about 10,540 meters. The Kermadec Trench, north of New Zealand, about 10,047 meters deep. The Puerto Rico Trench, the deepest point in the Atlantic Ocean, about 8,376 meters. The South Sandwich Trench, the deepest point in the Southern Ocean, each one a world of its own, each one a subduction zone, each one dark and cold and full of pressure and full of life. The physics of extreme depth, what pressure does to everything. Pressure, this is the defining characteristic of the deep ocean. And the Mariana Trench specifically, not the darkness, not the cold, not the depth itself, but what depth creates pressure. Water is heavy. A column of water 10 meters high exerts approximately 1 atmosphere of pressure. At bord, at the surface of the ocean, 1 bar of pressure. At 10 meters depth, 2 bars. At 100 meters, approximately 11 bars. At 1,000 meters, approximately 101 bars. At 10,000 meters, the approximate depth of the Mariana Trench floor, approximately 1,000 bars, 1,000 times the surface pressure. At null bar, in practical terms, if you filled a polystyrene foam cup, the kind you get with takeaway coffee with air at the surface, and lowered it to the bottom of the Mariana Trench, without allowing any air to escape or enter, the cup would be compressed to roughly 1/1000 of its original volume. It would become a tiny, dense, solid disk, barely recognizable as the object it was. This is not a thought experiment. It is something that deep-sea researchers actually do. They attach polystyrene cups to the outside of submersibles and ROVs and lower them to great depth to demonstrate pressure. And also, frankly, as a kind of art project, the cups come back compressed to beautiful, strange, small objects with all the drawings and writing made on them by researchers and school children preserved, miniaturized, concentrated, denser. What pressure does to water? Water is often called incompressible. This is approximately true at moderate pressures, but at the pressures found at the bottom of the Mariana Trench, water is compressible. The density of water at 10,000 meters is measurably higher than at the surface, about 5% denser. It has been compressed slightly by the enormous weight above it. This matters for organisms because cells are mostly water, and the water inside cells at the pressure of 10,000 meters is compressed slightly differently than at the surface. The membranes of cells made of phospholipid bilayers become stiffer, less fluid, less permeable to the molecules that need to cross them. For the cell to function, organisms that live at depth have adaptations to deal with this. Their membrane lipids are different. more fluid at high pressure. The enzymes in their cells are pressure adapted, function properly at 1000 bars, not at 1 bar. If you brought a Hadal organism to the surface, its enzymes would stop working, its membranes would become too fluid, the pressure adapted machinery would fail. In normal condition, the organism would die, not from low pressure, but from the cellular consequences of low pressure on biology that evolved for high pressure. Sound in deep water. Sound travels faster in denser water. Sound travels faster at higher pressure. Sound travels differently at different temperatures. In the deep ocean, all of these factors combine to create a complex acoustic environment. The deep sound channel SOFAR, which we mentioned in the Amazon episode, operates differently in the Hadal zone, where the high pressure increases sound speed, creating a specific acoustic profile that affects how sound travels and how Hadal organisms use sound, if they use it at all, light in deep water, or rather the absence of it. The photic zone, where sunlight penetrates the ocean enough for photosynthesis, extends to approximately 200 meters depth. In the clearest ocean water, in cloudier, more productive water, much less. Below 200 meters, no photosynthesis. Below 1,000 meters, no measurable sunlight at all. In the Mariana Trench, at 10,000 plus meters, the darkness is absolute. No photon of sunlight has ever reached this depth. Not since the trench was formed. Not once. In 50 million years, the only light that exists in the deep ocean is biological. Bioluminescence, light produced by living organisms through chemical reactions that generate photons without heat in the midnight zone between 1,000 and 4,000 meters. Bioluminescence is common. Many fish species produce light from photophores, light-producing organs, for camouflage, for communication, for hunting. The deeper you go in the midnight zone, the more dramatic the bioluminescent displays. Some organisms pulse, some streak light, some glow continuously. In the Hadal zone, below 6,000 meters, the character of life changes. The active swimmers of the midnight zone, the bioluminescent fish and squid, are mostly absent. What replaces them is different, more patient, more anchored to the sediment, more dependent on what falls from above. The Challenger Deep, the deepest known point, Challenger Deep. The name carries a particular resonance. It sounds like something from science fiction. The deep challenge, the ultimate challenge, the challenge of the deepest. But the name comes from HMS Challenger, the British research vessel that in 1875 first measured an extraordinary depth at this location. HMS Challenger was not built for the deep ocean. She was a Royal Navy corvette converted for scientific research. Her guns removed, her gun decks converted to laboratories and storage, with dredging equipment and sounding apparatus, and the instruments of 19th century oceanography. The Challenger expedition sailed from Portsmouth in December 1872 and spent almost 4 years at sea, covering 130,000 kilometers, making observations and collections across every ocean that laid the foundation for modern oceanography. On the 23rd of March, 1875, in the Western Pacific, the Challenger used a hemp line, weighted with lead, to sound the depth at a location in what we now know as the Mariana Trench. The line ran out to 8,184 meters without hitting bottom, a depth that was at that time the greatest ever measured. A depth that announced the existence of something extraordinary. In the Pacific floor, the Challenger expedition scientists did not fully understand what they had found. The technology to explore it, the submersibles and ROVs, the sonar and the cameras, none of it existed yet. They had found a number, a depth, a measurement, but the world at that depth was completely beyond their reach. The location was named Challenger Deep in honor of the ship and the expedition that first hinted at its existence. Modern measurement, the exact depth of Challenger Deep, has been measured many times. With improving precision, the most recent surveys using multi-beam sonar and pressure sensing instruments lowered to the floor give depths in the range of 10,902 to 10,935 meters. Different measurements give slightly different numbers because the trench floor is not flat and different instruments measure slightly different things. And the definition of sea level itself involves corrections for tides and atmospheric pressure. The most widely cited modern figure is approximately 10,935 meters, or 35,876 feet, give or take a few meters. This is the number we will use. This is the number that represents the deepest known point on the surface of the Earth. The first descent, Don Walsh and Jacques Piccard, January 1960, for the first 85 years after the Challenge expedition identified the deep. Nobody went there. Nobody had the technology. Nobody had the vessel. Nobody had perhaps the specific combination of engineering capability and human courage that it would require. Then in January 1960, two men went. Don Walsh, a United States Navy lieutenant, 26 years old at the time, Jacques Piccard, a Swiss engineer and oceanographer, 37 years old, son of Auguste Piccard, the famous Swiss physicist who set altitude records in high-altitude balloons, and who had designed the bathyscaphe, the deep-diving vessel that would carry his son to the bottom of the world. The vessel was the Trieste, not a submarine in the conventional sense. A bathyscaphe, a different kind of craft, designed specifically for extreme depth. A submarine uses pressure vessels to maintain a habitable internal space. The hull must withstand the pressure differential between inside and outside. At 10,000 meters, the hull would need to withstand 1,000 bars of external pressure while maintaining 1 bar internally, a differential of 999 bars across every centimeter of hull surface. The engineering demands are extraordinary. The Trieste solved this differently. Instead of maintaining a fully pressurized interior throughout a large vessel, the Trieste used a small, massively thick spherical capsule. For the crew, a sphere about 2 meters in diameter, with walls 12.7 centimeters thick, made of specially formulated steel, designed to resist the crushing pressure, attached below an enormous float, filled not with gas which would compress under pressure, but with aviation fuel, gasoline, lighter than water, even at the pressures of the deep ocean, providing the buoyancy that would keep the entire vessel positively or neutrally buoyant. To this end, the Trieste released the aviation fuel partially and attached iron ballast lead pellets to the underside. The extra weight pulled the vessel down to Ashend. The iron ballast was released. The vehicle became positively buoyant and rose without any propulsion system needed, just buoyancy. The basic principle of a lava lamp applied to the deepest point in the ocean. On the 23rd of January 1960, the Trieste began its descent from the surface of the Pacific Ocean above the Challenger Deep at Dependorblue 3 a.m. The descent took 4 hours and 48 minutes. They descended at a rate of about 1 meter per second. Not fast, but steady, downward through every layer of the water column. Walsh and Pickard communicated occasionally with the surface by acoustic phone, a hydrophone system that sent and received sound through the water column. The communications were difficult, delayed, as the sound had to travel thousands of meters in each direction. There were long pauses between transmission and receipt, between question and answer, the isolation of being 4 hours below, with communication that worked, but slowly, must have been profound. At 1:06 p.m., at the deepest measured point, the Trieste settled gently into the sediment at a depth of approximately 10,916 meters. Later refinements of the measurements would revise this number slightly. 2 human beings at the bottom of the Mariana Trench. For the first time in history, Walsh later described the moment of touchdown as quiet, gentle, the enormous vehicle settling into the pale sediment, raising a small cloud that hung in the water for a long time, before slowly settling back. The porthole, the small, thick porthole of the Trieste sphere, had developed a crack during the descent, not dangerous. The crack was in the outer acrylic cover, not the primary pressure vessel, but enough to be concerning, enough to limit the time they spent at the bottom. They stayed for 20 minutes. 20 minutes at the bottom of the world, looking out through the porthole, with a floodlight illuminating the immediate vicinity. And Walsh saw something in that 20 minutes that he reported with certainty, that was disputed by scientists for years afterward: a flatfish on the floor of the Challenger Deep, a Dunusens 7 metres, an animal with eyes in the spine and the basic vertebrate body plan, living where nothing with a spine should be able to live. Scientists were skeptical. The pressure should have been too extreme. For a vertebrate to function, the environment too harsh, the food too scarce for a fish, with the specific physiological demands of a fish to survive. Walsh maintained he saw it. He described it clearly: a flatfish, pale, on the sediment, watching the vehicle with the same interest that the occupants of the vehicle were watching it. Later, research would confirm that fish do exist in the huddle zone, not flatfish as Walsh thought he saw, but fish nonetheless. Snailfish, small, translucent, surprising. More on them shortly. Walsh's observation was not wrong, just slightly misidentified. The species he saw was probably a sea cucumber, or one of the other hadal organisms. That was unfamiliar. In the limited light, through a small porthole from a rocking vessel, in 20 minutes, at the bottom of the world, they ascended 3 hours and 15 minutes, back to the surface, back to sunlight, back to the world that makes sense to human bodies. Don Walsh lived to age 92, dying in November 2023. He spent his entire career in and around the ocean, advocating for deep ocean exploration, for the importance of understanding the world below that he had seen for 20 minutes. On a January afternoon in 1960, what lives at the bottom, the animals. Nobody expected. For a long time, scientists believed the deep ocean was largely empty, or at least sparsely populated by hardy, specialized bacteria, and perhaps a few simple invertebrates that could tolerate the extremes of pressure and cold and darkness. This belief was wrong, profoundly wrong. The deep ocean, including the Hadal zone, is full of life. Not full in the sense of a coral reef, not teeming with the visible diversity of a tropical ecosystem, but full in its own way, on its own terms, with organisms that have adapted so completely to the extremes of their environment that they are as extraordinary as anything in the natural world. The snailfish. Let's start here, because the snailfish changed everything about how we think of the limits of vertebrate life. Snailfish, Formiliparidae, a small, elongated fish with tadpole-like bodies, pale, almost translucent, soft, without scales, or with tiny embedded scales that you'd miss unless you were looking for them. In 2008, a lander, an unmanned vehicle equipped with cameras and bait, was deployed in the Japan Trench and photographed snailfish at a depth of 7,703 meters, the deepest fish ever recorded at that time. Then in 2014, the record was broken again. Snailfish photographed at 8,145 meters in the Mariana Trench. In 2017, a species named Pseudoliparus suirae was described from specimens collected in the Mariana Trench at depths up to 8,178 meters in 2023. A team of researchers from the University of Western Australia, led by Alan Jameson, deployed a lander in the Izu Ogasawara Trench, south of Japan, and filmed the snailfish at 8,336 meters, the deepest fish ever recorded. 8,336 meters. A vertebrate with a brain, with eyes, with fins and a tail and a digestive system, living, hunting, presumably reproducing at 8,336 meters, under approximately 836 bars of pressure. How? The snailfish has several key adaptations to MAO, trimethylamine oxide, a compound found in the tissues of marine fish that stabilizes proteins at depth. At high pressure, the molecular machinery of cells, the proteins that catalyze chemical reactions, the enzymes tend to be destabilized. Their shapes change. They stop working properly. This is the fundamental physiological challenge of depth. TMAO counteracts this. It stabilizes protein structure, keeps the enzymes functional at pressures that would destroy the protein function of surface-dwelling fish. Snailfish have the highest TMAO concentrations of any fish studied, and the concentration increases with depth. Fish collected from 8,000 meters have more TMAO in their tissues than fish from 4,000 meters, which have more than fish from 1,000 meters. The deeper you go, the more TMAO you need. And the snailfish are pushing that relationship to its apparent limit. There may be a maximum depth below which TMAO can no longer stabilize proteins effectively, below which no fish can survive. That depth, based on the physics, has been calculated at approximately 8,200 to 8,400 meters. The snailfish, photographed at 8,336 meters, may be near the absolute limit for vertebrate life as we currently understand it. The appearance of Hadal snailfish is striking. They are pale, almost white, almost transparent. You can see their internal organs through their skin. Their eyes are visible, small, functional, but perhaps less relied upon in the darkness than the lateral line system. The pressure-sensitive receptors along their sides that detect water movement and vibration, the approach of prey, the presence of other animals in the dark, the amphipods. If the snailfish are the surprising vertebrates of the Hadal zone, the amphipods are the characteristic Hadal animals, the ones that define the zone, that are found in abundance in every Hadal trench, that apparently thrive at pressures that defeat most organisms. Amphipods, crustaceans, roughly shrimp-like in appearance, though not closely related to shrimps. Small, most species a centimeter or two in length. But in the Hadal zone, the amphipods are not small. They are giant by amphipod standards. Hirundella gigas, the most studied Hadal amphipod, collected from the Mariana Trench and other Hadal sites, reaching up to 3.4 centimeters in body length, more than twice the size of typical shallow water amphipods. And Elisella gigantea, the giant deep-sea amphipod, reaching 28 centimeters. In some specimens, 28 centimeters, that is nearly the size of your forearm. For an amphipod, in a group where typical species are measured in millimeters, the deep-sea giants are extraordinary. Why do animals get larger at depth? This is an old observation called deep-sea gigantism, and it applies to many groups, not just amphipods, isopods, sea spiders, various worms, various other invertebrates get larger in the deep sea than their relatives at the surface. Several hypotheses. Cold temperature slows metabolism. Larger size is one solution to cold. Larger animals have more thermal inertia. They don't lose heat as quickly. In the deep sea, food is scarce. Arriving as marine snow, the constant fall of organic particles from above, a larger body can go longer without food. A larger body can store more energy between meals, and in the absence of many predators, the evolutionary pressure towards small size, that small size provides speed to escape predators, is reduced. Animals can afford to grow large without the cost of being slow. Hirundella gigas specifically has been studied intensively because it is so abundant in Hadal trenches and because its biology illuminates the extraordinary adaptations of Hadal life. Hirundella gigas its wood, specifically cellulose, from wood that is sunk to the trench floor. This sounds mundane until you consider what it requires. Cellulose, the structural carbohydrate of plant cell walls, is extremely difficult to digest. Most animals cannot digest it directly. They rely on gut bacteria or protists to break it down for them. But Hirundella gigas produces its own cellulase enzyme genetically in its own cells. without relying on gut symbionts. It digests wood directly. This is extraordinarily rare. In animals, a few other species can do it, but it is not common. And the fact that the hadal amphipod has evolved this capacity tells us something about the food resources of the deep trench. Wood sinks, waterlogged, dense after long immersion, and it arrives at the trench floor, occasionally, irregularly. But it arrives, and when it does, Hirondiala yigas eats it. The sea cucumbers in the deepest parts of the Mariana Trench. One of the most numerous animals is the sea cucumber Holoturian. Sea cucumbers are echinoderms, related to sea stars and sea urchins, but elongated, soft-bodied, moving slowly across the seafloor, ingesting sediment, extracting the organic matter from it, and excreting the cleaned sediment behind them at hadal depths. Sea cucumbers can be remarkably abundant. In some surveys of the Challenger Deep, sea cucumbers have been the most visible macrofaunal organisms, moving slowly across the pale sediment in extraordinary numbers. What do they eat? The organic matter in the sediment, the marine snow that has fallen from above, the bacteria in the sediment, the accumulated debris of the lives lived in every ocean above them. The sea cucumbers are the recyclers of the deep, processing the sediment, extracting what nutrition it contains, and leaving behind something cleaner, something that has been processed, something that has passed through a body and been changed by it. The xenophyrophores, one of the most extraordinary organisms of the hadal zone, is not well known outside deep sea biology. The xenophyrophores. Xenophyrophores are single-celled organisms, giant single-celled organisms, single cells that can grow to 20 centimeters across, 20 centimeters. For a single cell, the largest single cells in the world. By some measures, they are foraminifera, amoeba-like organisms, with a test, a shell-like structure built from sediment particles cemented together into a complex, branching, irregular shape that the single cell inside fills, extending its cytoplasm throughout the structure. Xenophyrophores are found throughout the deep ocean, but they are particularly abundant in trenches, in the hadal zone, where they can carpet the seafloor. In patches of extraordinary density, they may form the structural basis for a microhabitat, a reef of sorts, made of single-celled organisms that other hadal species live within and around. These xenophyrophores, as ecosystem engineers, in the deep, the hadal food web, what eats what in total darkness. The fundamental question of any ecosystem is energy. Where does the energy come from? What is the base of the food chain? In surface ecosystems, the answer is sunlight, photosynthesis, plants and algae capturing solar energy, converting it to chemical energy in the form of glucose that everything else in the ecosystem ultimately depends on. In the deep ocean, there is no sunlight. There is no photosynthesis. The food energy must come from somewhere else. Marine snow, the primary food source for the deep ocean, is marine snow, the constant, slow, steady fall of organic particles from the surface ocean downward through thousands of meters of water to the sediment below. Marine snow consists of many things: dead organisms, plankton, that lived and died in the surface waters, fecal pellets from zooplankton, small packages of organic material, dense enough to sink, mucus aggregates, transparent, complex particles made of mucus secreted by various marine organisms, bound to other particles, creating larger, heavier aggregates that sink faster, bits of larger organisms, fragments of jellyfish, fragments of fish, fragments of everything that lives and dies in the upper ocean. Marine snow is not uniform. It has a seasonal signal in the spring and summer, when the surface ocean is productive, when phytoplankton bloom, more material is produced, more sinks. In the autumn and winter, when production slows, the snow thins. The deep ocean, even at 10,000 meters, feels the seasons, delayed by weeks or months as the signal propagates downward, but feels them. Food falls. In addition to the constant background of marine snow, the deep ocean receives occasional large food falls, whale falls. When a whale dies at the surface or near the surface, its body sinks over hours to days, depending on the depth of water it sinks through and the density of its body. A large whale carcass arriving at the deep ocean floor is an extraordinary event for the organisms there, an enormous pulse of food in a world of scarcity. The whale fall is immediately colonized, first by mobile scavengers, sleeper sharks, hagfish, mobile crabs, and amphipods that descend on the carcass and eat the soft tissue rapidly over days to months, stripping the carcass to the skeleton, then by enrichment opportunist species that colonize the altered sediment around the carcass, taking advantage of the enriched organic material that the soft tissue decomposition has added to the sediment. Then by the sulfophilic stage, the most remarkable, when the lipids, the fatty material in the whale bones, are decomposed by bacteria in an anaerobic process that produces hydrogen sulfide. The hydrogen sulfide supports chemosynthetic bacteria, the same basic metabolism that powers hydrothermal vent communities. The bacteria oxidize the hydrogen sulfide for energy and support a community of organisms that live around the bones in a process that can last for decades, sometimes for a century, as the lipid reserves of the whale bones are slowly consumed. A whale fall is not a single event. It is a succession, a sequence of communities, each one replacing the last. Over years and decades, a slow ecological unfolding in the deep wood falls occur similarly. When waterlogged wood sinks to the deep ocean floor, wood is rich in cellulose and lignin, complex organic molecules that require specific bacteria to break down, but that contain significant energy. When they are broken down, wood falls support their own succession of communities, with specific wood-boring bivalves, shipworms that eat the wood, creating burrows that other organisms colonize. And eventually, as the wood is consumed, a chemosynthetic community. If sufficient sulfide is produced, chemosynthesis in the hadal zone, at hydrothermal vents, in mid-ocean ridges, hot chemically enriched fluid emerging from the ocean floor supports communities entirely independent of sunlight, chemosynthetic bacteria that oxidize hydrogen sulfide or methane or other reduced compounds for energy that support food webs of extraordinary complexity, entirely in the dark, entirely independent of the surface world. In the Hadal zone, chemosynthesis is less dominant than at vents, but it is present in cold seeps, places where methane and hydrogen sulfide seep from the sediment. At some Hadal trench sites, communities of chemosynthetic bacteria and the animals that feed on them exist, extending the food web beyond the rain of marine snow, the chemistry of abyssal water, what the deep ocean is made of. The water in the Mariana Trench is not like the water at the surface, not just in temperature and pressure, but in chemistry, oxygen. The deep ocean is not anoxic, not oxygen-free. This surprises people because they might expect that cut off from the surface, from photosynthesis, from the oxygen-producing primary producers, the deep ocean would run out of oxygen. It doesn't because of thermal circulation. The global ocean circulation system, driven by temperature and salinity differences, that drives cold, dense, oxygen-rich water from the polar regions down into the deep ocean, carrying oxygen to the abyss. The process at high latitudes in the Arctic and Antarctic, cold air chills the surface water, which becomes denser and sinks, carrying with it the oxygen dissolved at the surface. This dense, cold, oxygenated water sinks to the bottom and spreads slowly along the ocean floor, carrying oxygen to every depth of every ocean, including the Mariana Trench. The deep Pacific water is well oxygenated, not as oxygenated as surface water. The oxygen content decreases with depth as it is consumed by respiration, by the organisms in the water column, but not depleted. Enough remains to support the life we find there. Dissolved minerals. The deep ocean is rich in dissolved minerals. Manganese, iron, copper, cobalt, nickel. These accumulate in the deep ocean from the weathering of ocean floor rock, from the hydrothermal vents, from the dissolution of sinking particles. In the deep Pacific, these minerals precipitate, form nodule, manganese nodules, potato-sized lumps of mixed metals. On the abyssal plain and in the trenches, these nodules are of intense commercial interest because they contain valuable minerals in concentrated form on the ocean floor. Deep sea mining, the extraction of these nodules, is being seriously proposed by commercial interests in multiple countries. The nodules in the Clarion-Clipperton zone in the Pacific contain more cobalt and nickel and manganese than all the currently known terrestrial reserves combined, but mining them would devastate the ecosystems of the deep ocean floor. The disturbance of the sediment, the noise, the light, the disruption of the food web that depends on the undisturbed sediment would affect deep sea communities over vast areas for decades, potentially centuries. Given how slowly these ecosystems regenerate, the conflict between the mineral wealth of the deep ocean and the ecological value of its ecosystems is one of the major environmental debates of the coming decades. And the Mariana Trench, as a symbol of the unexplored deep, is at its center. Plastic at the bottom, what we put there In 2018, researchers from Newcastle University deployed landers in the Mariana Trench, collected amphipods from depths of 6,000 to 11,000 meters, and analyzed their gut contents. In every specimen, from every depth, they found plastic fibers, microplastic, in the bodies of animals. At the deepest point in the ocean, this was not entirely unexpected. Plastic has been found throughout the ocean, from the Arctic ice to the Antarctic sediment, from coastal beaches to open ocean surface. Plastic is everywhere, but the Hadal zone, the most remote, the most isolated, the deepest, the most inaccessible, the place furthest from any human activity, was not free of it. The plastic had found its way through thousands of meters of water to the bodies of animals living in the darkness. At the bottom of the world, in 2019, Victor Vescovo, a private explorer who had descended to the Challenger Deep in a submersible called the DSV Limiting Factor, part of the 5 Deeps expedition, to visit the deepest point in each ocean, reported seeing a plastic bag at the bottom of the Challenger Deep, a plastic bag, a 2,935 meters. At the deepest point on the surface of the Earth, the bag had traveled from somewhere, the surface where someone had discarded it, or it had blown into a river, or fallen from a boat, or been washed from a beach, carried by the currents to the middle of the Pacific, waterlogged, dense enough to sink, slowly through the water column, 10,000 meters, to the bottom where it was found by a man in a submersible who had spent millions of dollars to go where almost no one had gone, and found a plastic bag. Microplastics, even where plastic bags are not visible, are present. In the sediment of the Mariana Trench, studies have found plastic concentrations in trench sediments that are higher than in some coastal areas because the trench is a sink. Sediment and particles are funneled into it from the surrounding ocean, concentrating what the ocean carries. The plastic carries chemicals, persistent organic pollutants, PCBs, DDT and its breakdown products, other industrial chemicals that were banned or restricted decades ago. But that persist in the environment for decades or centuries, absorbed to the surface of plastic particles, carried to the deep where they enter the food web through the organisms that eat the plastic directly or indirectly. The Hadal zone is contaminated. Nordpristine, the most remote ecosystem on Earth, bears the chemical signature of the industrial world of the 20th century, of the decisions made at the surface about how to produce and discard things that have consequences, all the way to the bottom of the deepest ocean. The human expeditions, everyone who has gone there. How many people have been to the Challenger Deep? As of 2024, approximately 30 people. In the entire history of human exploration, in the 64 years since Don Walsh and Jacques Picard first descended, 30 people have visited the deepest point on Earth. Compare that to space. More than 600 people have been to space. More than 612 people have walked on the moon. More people have been to space than have been to the bottom of the Mariana Trench. This reflects the difficulty and the cost of deep ocean exploration. Going to space is hard, but the engineering is at least familiar. We know how to create pressure vessels. we know how to manage life support. We have been doing it for decades. Going to 11,000 meters of ocean presents different engineering challenges, different material challenges, different logistical challenges. The vessels that have made the descent, Trieste 1,960, Walsh and Picard. The first, Kaiko 1,995, an unmanned Japanese ROV, reached 10,911 meters, the deepest unmanned descent at that time. Deep Sea Challenger 2012, James Cameron, the film director. In a submersible he commissioned specifically for the descent solo. He spent about 3 hours at the bottom, collecting samples and filming. He described the bottom as barren, desolate, lunar. DSV, limiting factor, 2019. Victor Vescovo, part of the Five Deeps expedition, the most thorough recent exploration. Victor Vescovo's expedition deserves particular attention because it was the most systematic, the most complete, the most productive scientifically. Vescovo made multiple dives to the Challenger deep, not just one. He spent extended time at the bottom collecting samples, using manipulator arms on the submersible to take core samples and biological specimens. His team discovered several new species, a new snailfish species, new amphipod species, and confirmed the presence of plastic, including the plastic bag he reported. The DSV limiting factor is a full ocean depth submersible capable of reaching any point in the ocean, at any depth, certified for repeated dives, not a one-time vehicle, a reusable research tool. It was later purchased by the Ocean Research Foundation Inc. Fish and continues to be used for deep ocean exploration, the most capable crewed deep ocean vehicle currently in service. Part 12. What the trench tells us about the planet. Deep time written in rock. The rock of the Mariana Trench is not young. The Pacific Plate in the region of the Mariana Trench is approximately 180 million years old. 180 million years. The rock on the floor of the Pacific Ocean in the Mariana Trench area was formed when dinosaurs were alive, in the mid-Jurassic, when Pangaea was breaking apart, when the Atlantic Ocean was just beginning to open. As the Pacific Plate moves westward, the rock that makes up the subducting portion gets older and older. It formed at the East Pacific Rise, the spreading center in the Eastern Pacific, where new ocean floor is created by volcanic activity. As the plates spread apart, new ocean floor forms in the east. Old ocean floor is consumed in the west at the Mariana Trench, a conveyor belt of rock, 180 million years from creation to destruction. The study of this rock, of the isotopic composition, of the minerals, of the chemical signals preserved in the rock, tells us about the history of the planet, about the ancient ocean, Abu Ancien Climat, about the movement of material through the Earth's interior over hundreds of millions of years. When the Pacific Plate subducts, it carries material into the mantle, including water locked in minerals, carbon, in carbonate minerals, sulfur, various trace elements. These are returned to the Earth's interior through the subduction process and eventually recycled. through volcanic activity back to the surface. In a different form, the trench is a window into this recycling, into the long-term geochemical cycles that regulate the chemistry of the ocean and the composition of the atmosphere over geological time. The trench is not just a feature, it is a process, a valve in the planetary plumbing system that has been operating for 50 million years. The life nobody expected. More on the Hadal ecosystem. Let me tell you about more of the creatures, because there are more, many more, in the darkness of the Mariana Trench. Polychaete worms, abundant at all ocean depths. In the Hadal zone, several species are found at extreme depth, robust, segmented worms that burrow in the sediment or live at the surface, moving slowly across the pale floor. The Hadal polychaetes are not identical to their shallow water relatives. They have adaptations for pressure, for the cold, for the specific food resources of the deep trench, but they are recognizably worms, moving with the same basic mechanism that polychaete worms have used for 500 million years. In every ocean, at every depth, foraminifera, single-celled organisms, already mentioned as the source of much of the trench sediment, but also alive in the trench as a living component of the Hadal ecosystem, living foraminifera in the Hadal zone have been found at the greatest depths, even in the Challenger Deep, living, moving, feeding, building their tests from sediment particles in the darkest, coldest, most pressurized waters. On the surface of the earth, the hagfish, perhaps the most unlikely of the deep ocean's inhabitants, in some ways, hagfish, Myxini, are not fish, not technically. They lack a jaw. They have no vertebral column, are notochod, but not vertebrae. They are the most primitive vertebrate-like animals, the most ancient lineage in the group that includes all vertebrates. Hagfish are found throughout the deep ocean, including in Hadal trenches, though they are more common at the upper end of the Hadal zone and in the deep sea above than in the deepest trenches. The hagfish are extraordinary for several reasons. They are scavengers, among the most effective in the deep ocean. When a whale falls or a fish dies, the hagfish arrive quickly and consume the organic material, not just by eating it, but by burrowing inside the carcass, eating from within. They produce slime in extraordinary quantities when threatened. A single hagfish can produce several liters of dense, incredibly viscous slime in seconds. The slime expands when it contacts seawater, filling the mouth and gills of any predator attempting to bite the hagfish, a defensive mechanism of almost perfect effectiveness. They can tie themselves in knots. Literally, when a hagfish is in a confined space, or when it needs to generate leverage to pull itself free of something, it ties its flexible body into a knot, passes the knot along its body to generate force, a remarkable, disconcerting behavior that has no parallel in any other animal. The giant isopod, Bathynomus giganteux, related to pillbugs, the small crustaceans that curl into a ball when disturbed, found under stones in gardens. In the deep sea, the pillbug grows large, very large, A giant isopod can reach 76 centimeters, 3/4 of a meter. For an animal related to a garden pill bug, this is extraordinary. Giant isopods are found throughout the deep ocean, from about 170 meters to over 2,100 meters. They are scavengers and occasionally predators of slow-moving invertebrates. They can go without food for extended periods, up to 5 years in captivity, without feeding and surviving, a capacity for fasting. That reflects the irregular feast and famine existence of the deep-sea scavenger, waiting for the next foodfall. The philosophy of depth, what the trench means. I want to stay here for a moment, not with the science, with the feeling. The Mariana Trench is the farthest removed place from human experience on this planet, the most extreme, the most inaccessible, the most unlike anything we evolved to understand or inhabit. And yet it is here, on the same planet, under the same sky, in the same world. The water at the surface of the Pacific Ocean above Challenger Deep is the same ocean as the water on a beach in California, or the water lapping at the shore of the Maldives, or the water you can see from any coastal cliff. The same molecules, the same ocean, 11 kilometers shallower and 11 kilometers closer to the sky. When I think about the Mariana Trench, I think about scale, about how the world contains things that are completely beyond the reach of our senses, our intuition, our evolutionary heritage. Nothing in the history of human evolution prepared us for the concept of 11,000 meters of water above us, of 1,000 bars of pressure, of total permanent darkness. In a world where nothing has ever seen the sun, these things exist on our planet, not in some distant galaxy, not on a hypothetical alien world. Here, now, 50 million years old, full of life, full of things we haven't found yet. The Mariana Trench is a reminder that the world is larger and stranger and more full than we usually imagine, that the known is a small island in an ocean of the unknown, and the ocean is very deep. This could be frightening, the vastness of the unknown, the depth of what we don't understand, or it could be the opposite, the recognition that there is more, always more, that the world is inexhaustible, that every expedition, every lander, every new instrument will find something new, something unexpected, something that changes our picture of what the deep is and what it contains. The snailfish at 8,336 meters was unexpected. The wood-eating amphipod was unexpected. The xenophyrophores covering the trench floor were unexpected. The plastic bag was deeply unwelcome, but not unexpected. And the next expedition will find something else unexpected, something that nobody predicted, something that changes the story again. This is the gift of the deep ocean. It keeps producing surprises. It keeps resisting complete understanding. It is, in the most literal sense, inexhaustible. There's always more, always deeper, always something new. In the darkness, the sound of the deep, acoustic life in the abyss. The deep ocean is not silent. This surprises people. Silence seems like the obvious state of a world without wind, without waves, without the rustle of leaves or the call of birds. But the deep ocean has its own soundscape generated by the physics of the water itself and by the organisms that live in it. the SOFAR channel, the deep sound channel that we mentioned in the Amazon episode, concentrates sound energy at the depth where sound speed is at its minimum, around 1,000 meters in the Pacific. Sound that enters the channel is trapped and propagates for extraordinary distances with minimal energy loss. Whales use the SOFAR channel to communicate across entire ocean basins. A blue whale song produced in the North Pacific can be detected thousands of kilometers away. In the SOFAR channel, the channel is a communication network for the largest animals on Earth. In the Hadal zone, below the SOFAR channel, the acoustic environment is different. Sound still travels, but the characteristics change. With depth and pressure, the organisms that use sound at Hadal depths, if they do, have their own specific acoustic environments, their own specific challenges. Seismic noise. The Pacific Ocean is seismically active. The subduction of the Pacific Plate beneath the Mariana Plate generates earthquakes regularly. The friction of the plates, the snap of rock under accumulated stress, the release, these earthquakes produce sounds that propagate through the water as well as through the rock, low frequency sounds that the deep ocean transmits efficiently. Animals in the deep ocean live in a world punctuated by seismic sounds that we have never cataloged, never fully described, that may affect the behavior and the ecology of Hadal organisms in ways we don't understand. There's so much we don't understand about the acoustic world of the Mariana Trench, about the sensory lives of the organisms there, about how they perceive their world, about what their world sounds like to them. The closing thought, the patience of the deep. The Mariana Trench has been here for 50 million years. In 50 million years, it has been visited by humans for a total of a few dozen hours by approximately 30 people in vehicles that could stay for hours at a time. At most, the trench existed before any of the continents were in their current positions, before the Himalayas rose, before the Alps, before the Andes reached their current height, before any of the mountain ranges that define the topography of the modern world. The trench existed when our primate ancestors were just beginning, when the first great apes were diversifying in Africa, when the world was warm and the poles were forested, and nothing yet had the cognitive equipment to ask, what is down there? The organisms in the trench have been evolving continuously for those 50 million years in their specific, extreme, dark, cold, pressurized world, adapting to conditions that change on geological timescales. If they change at all, they have not needed us. They will not need us. Whether we go back or not, whether we understand them or not, whether we name them or not, they will continue as they have continued for 50 million years. But we need them, or at least we need what they represent, the recognition that life is more adaptable, more pervasive, more extraordinary than any prior model of its limits suggested. Every time we've thought we knew where life couldn't exist, we've been wrong. The boiling water of hydrothermal vents, where temperatures exceed 400 degrees Celsius, life, the frozen lakes beneath Antarctic ice, life the hypersaline waters of evaporating salt flats, life, the acidic hot springs of Yellowstone, life, the dry valleys of Antarctica, where liquid water is almost never present, life, the rock kilometers below the Earth's surface, life, and the Challenger Deep, 10,935 meters below the surface of the Pacific, where the pressure is 1,000 bars, and the temperature is 2 degrees above freezing, and no light has ever penetrated. Life, the Hadal Zone, is not the limit. It is just the limit we know about today. And tomorrow, someone will lower a lander into a trench we haven't studied yet, or deeper into one we have, and find something that changes the sentence, that changes what we think. The limit is the sleep sequence going deeper than thought, and now we let the depth do its work. The Mariana Trench has been here, in the dark, for 50 million years, without your attention, without anyone's attention, moving slowly, consuming the Pacific plate, centimeter by centimeter, year by year, patient beyond any word. We have for patience. The pressure at 10,935 meters is 1,086 times the pressure of the air around you right now. In this room, you cannot feel the difference between 1 bar and 1,086 bars. Not from here, not from the surface. The difference is abstract, a number, but for the amphipods moving across the pale sediment at the bottom of the world, that pressure is simply the world, the only world they know. Normal, complete, the world as it has always been. Let the weight of the day settle the way sediment settles in still water, not fighting, not resisting, just settling slowly through the water column, grain by grain, layer by layer, until it rests on the floor, the darkness at 10,935 meters. Is total, not the darkness of a room at night where your eyes adjust and you begin to see shapes and outlines and the familiar geometry of your space. The darkness of the Challenger Deep is the darkness of no photon ever in 50 million years. Not one, the absolute zero of light. And yet in that darkness, life, the snailfish, its translucent body moving through the absolute dark, finding prey, through the pressure sensors of its lateral line, through the chemistry of the water, around it, navigating a world that has never been illuminated, that was never designed to be seen, that simply is. In the dark, let your eyes close. If they haven't already, let the light of wherever you are, further into the back of your attention. Let the room become background. Let the sounds, whatever they are, become the sound of water, moving slowly. In the deep, the foraminifera are settling above you in the imagined water column, falling from the sunlit world above, down through the zones, the photic zone, the twilight, the midnight, the abyss, each one a tiny shell of calcium carbonate, drifting downward at perhaps a centimeter per day, taking years to travel from the surface to the trench floor, a slow rain of the dead that has been falling for 50 million years, building the sediment, one shell at a time. You are the surface. The snailfish is the deep, between you and it, 10,935 meters of water, of zones, of pressure gradients, of darkness deepening into absolute darkness, of temperature dropping to the cold that has been constant for millions of years. Between you and it, a world that exists. Whether you think about it or not, the amphipods are moving across the sediment. Right now, in the real world, in the actual trench, in the Pacific Ocean, while you breathe, while you drift, while the thoughts slow, the amphipods are moving, their small legs propelling them across the pale floor, searching for the organic particles that the marine snow delivers. Patient, in the dark, in the cold, in the pressure that is simply their world, the xenophyophores, the giant single cells are spread across the sediment. Right now, their cytoplasm filling the complex structures of their shells, single cells, 20 centimeters across, living in the most extreme environment on the surface of the earth, living so slowly that you could watch them for hours and see almost no movement, living on a time scale so different from yours that the comparison barely makes sense, that you're breathing slow, too much, something deeper, something more patient than your ordinary breath. In, long, the way water moves in the deep Pacific current that carries cold polar water down into the abyss slowly over decades. A single molecule of water may take hundreds of years to travel from the polar surface to the floor of the Mariana Trench. Hundreds of years for one journey, one direction, in the dark and out, releasing the way sediment releases when it finally settles, after floating in suspension for a very long time, just settling, finding its level, finding its rest. The trench doesn't know that you are thinking about it. The amphipods don't know that someone on the surface is lying still in a room somewhere on the landmass they will never reach, thinking about their lives, finding something in their lives that has meaning for a human trying to sleep. The trench is indifferent, but not in a cold way, in the way that very ancient things are indifferent to the brief, in particular, the way a mountain is indifferent to the clouds that pass across it, the way the ocean is indifferent to the storms at its surface, not hostile, not uncaring, simply larger than the things that concern it. The Mariana Trench is 50 million years old. You are some number of years that is not 50 million. The trench has been here since before your species existed, since before any species like yours existed. It will be here. As the Pacific Plate continues its slow consumption, the trench will deepen or shallow or shift over millions more years, regardless of what happens. At the surface, this is not a sad thought. It is a freeing one. The trench does not require your maintenance. The deep does not need your attention to continue being what it is. It simply is, as it has always been, and your brief, warm, pressurized at only one bar life at the surface is happening alongside it simultaneously. The deep and the surface, the trench and the room, the snailfish and you, both alive, right now, on the same planet, in the same ocean, at different depths, both real, both specific, both extraordinary, in their own terms. Part 13, the future of deep exploration, what comes next in the darkness. The Mariana Trench has been visited by 30 people in 64 years. In the next 64 years, that number will grow, not to million, not to thousands. The trench is not Everest. It will never be a destination. For amateur adventurers, the engineering required is too demanding, the cost too high, the margin for error too small, but it will be visited more systematically, more completely, more productively than it has been so far. The robots will go first. They already have unmanned landers, drop from surface ships, descend under their own weight, spend days on the bottom, filming, sampling before their ballast drops, and they rise to the surface to be recovered. These landers are becoming more sophisticated. Each generation, better cameras, better sample collection, better sensors for the chemical environment, for the acoustic environment, for the physical conditions of the Hadal zone, the autonomous underwater vehicles, the AUVs are the next step. Robots that can navigate under their own programming without a tether, without real-time human control, following a pre-programmed mission, mapping the seafloor in 3 dimensions at resolutions that no surface ship sonar can achieve. The Nearite under ice system, designed for under ice exploration in the Arctic and Antarctic, has been adapted for deep sea work, operating at extreme depths on a fiber optic tether, so thin that it has almost no effect on the vehicle's movement. The tether carries high bandwidth data, video, control signals to and from the surface, while the vehicle explores. Future vehicles will go deeper, faster, more often, will stay longer, will collect more samples, map more of the trench floor in higher resolution. The scientific questions are as specific. What is the full species list of the Mariana Trench? We don't know. We have sampled a tiny fraction of the trench floor in the most limited way. What lives there that we haven't found yet? We genuinely don't know. What are the microbial communities of the Hadal sediment? We have some data from some locations, but the trench is 2,550 kilometers long. We have sampled a handful of points. The microbial diversity along its length, in its different depths, in its different geological contexts, is almost entirely unknown. What is the role of the trench in global biogeochemical cycles? How much carbon is delivered to the trench by marine snow? How much is processed by the Hadal organisms? How much is eventually subducted with the Pacific plate, taken back into the mantle? These questions have implications for understanding the global carbon cycle and the ocean's role in long-term climate regulation. The trench is a player in the planetary carbon budget that we have barely begun to quantify. What happens to plastic and other pollutants in the Hadal zone? Are they being processed by the microorganisms? Are they entering the food web in ways we haven't tracked? Are they being transported into the subducting plate? And if so, what happens to them? In the mantle, these questions matter, not just academically, but for understanding the fate of the pollution that humanity has deposited in the ocean over the last century. Part 14, the pale sediment, a meditation on what the trench floor looks like. Let me describe the floor of the Challenger Deep as it has been described by the people who have been there. The sediment is pale, almost white in the light of the submersible's floods, but pale with depth, the color of very fine flour, or of chalk, or of the lightest possible dust. It is the compressed and partially cemented remains of foraminifera and other calcareous organisms that have been raining down from the surface ocean. For 50 million years, the surface of the sediment is soft. In photographs taken by landers, you can see the marks left by passing animals, tracks in the sediment, the trails of sea cucumbers moving across the floor, the disturbance left by amphipods feeding the small craters, left by organisms that emerged from the sediment and returned. The sediment has texture. It is not perfectly flat. There are small mounds built by infaunal organisms, organisms that live within the sediment, that process it, that rework it. From below, there are depressions where the sediment has been disturbed and not yet settled. The floor is alive. In the most literal sense, the sediment is reworked continuously by the organisms that live in it and on it. When a submersible lands, the disturbance of the sediment creates a cloud that hangs in the water for a long time because there is no current, no turbulence, no mixing to disperse it. The cloud from a single landing may persist for hours before settling back in the absolute stillness of the deepest water on Earth. James Cameron, who descended in 2012, described the floor as barren and lunar and desolate. This was his impression in the specific light of his submersible's floods in a limited area for a limited time, but the landers that have spent days on the floor tell a different story. The amphipods appear within minutes, attracted by the bait, dozens of them, then hundreds moving across the sediment with surprising speed. The sea cucumbers move slowly past. The rare snailfish appears occasionally, looking at the camera with its small eyes. The floor is not empty. It is not barren. It is quiet, in the way that very deep places are quiet, in the way that deserts are quiet, not empty, but sparse, with long distances between encounters, with life moving slowly on its own terms. In the distance, beyond the reach of the submersible's lights, the darkness is absolute. The floor extends in every direction for kilometers, covered in the same pale sediment, with the same slow life moving across it without any light, without any need for light. The light that the submersible brings is alien to this place, temporary, intrusive. The darkness is the normal. The darkness is the permanent state that everything here has adapted to for millions of years. When the submersible leaves, when the lights go out, the darkness returns. Immediately, completely, the pale sediment is invisible again. The sea cucumbers move in the dark as they have always moved. The amphipods disperse from the side of the bait into the dark in every direction. The cloud of disturbed sediment continues to settle slowly in the absolute stillness, and the trench is as it was before the submersible came, dark, cold, patient, alive in its own specific, extraordinary way. Part 15. The chemistry of life at depth, how biology reinvents itself under pressure. Let me go deeper into the biology of what it means to be alive at 10,935 meters, because the adaptations are not just interesting, they are philosophically significant. They tell us something about the nature of life itself, about its flexibility, about the range of conditions under which the basic processes can continue. Every living cell is a chemical factory, a collection of chemical reactions happening simultaneously, each one catalyzed by a specific enzyme. Each enzyme, our protein, folded into a specific shape that allows it to bind to specific molecules and facilitate the transformation of those molecules into other molecules. Enzymes are sensitive to temperature, to pH, to pressure. Change any of these, and the enzyme's shape changes. The binding site distorts, the catalytic activity decreases or stops. The cell stops functioning. The organism, this is why life has a temperature range and a pH range and a pressure range outside of which it cannot survive. The chemistry breaks down, the enzymes stop working, the reactions stop happening, the cell loses the ability to maintain itself against the second law of thermodynamics, which always wins, eventually. But the range is not fixed. It is adaptable, given enough time, given enough generations, given enough evolutionary pressure. The enzymes themselves can change, the proteins can evolve, new amino acid sequences that fold differently, that maintain their functional shape under conditions that would destroy the original sequence. Tomorrow, trimethylamine oxide is one solution, a chemical additive to the cell's environment that stabilizes protein structure against the pressure. The TMAO molecules interact with water molecules in the cell in a way that counteracts the effect of pressure on protein folding. It is a chemical buffer against the physical force of the deep, but TMAO is not free. It costs energy to produce and to maintain in the concentrations needed at depth. This is a tax paid by every Hadal organism that uses it. A metabolic cost of living deep. Membrane lipids are the other major adaptation. The membranes of cells are made of phospholipid bilayers, two layers of lipid molecules arranged with their hydrophilic heads facing outward into the water, and their hydrophobic tails facing inward into the membrane. At high pressure, these membranes become stiffer, more rigid, less permeable, the molecules that need to cross the membrane, the nutrients coming in, the waste going out, the signals being transmitted, have difficulty getting through. Adult organisms have a membranes with higher proportions of unsaturated fatty acids. In their lipid tails, unsaturated fatty acids have kinks in their chains that prevent tight packing, that maintain membrane fluidity. Even at high pressure, the membrane stays functional, where a shallow water membrane would become rigid and impermeable. These adaptations did not appear overnight. They evolved over millions of years of selection in a progressively deepening environment, or in an environment that started deep and stayed deep. The organisms that happen to have higher TMAO production or more unsaturated membrane lipids survived better in the deep conditions and passed those traits to their offspring, generation by generation, for millions of years, until the modern huddle organisms are as well adapted to 10,135 meters as any surface organism is to one atmosphere. This is evolution, working on biology at the extreme, using the same tools that it uses everywhere: variation, selection, inheritance, time, an enormous amount of time. Part 16, returning to the surface. What the trench gives us when we leave every expedition that has gone to the deep has brought something back. Not just samples, not just data, but a changed perspective on what the world is and what life is and what our place in both might be. Don Walsh came back from the Challenger Deep in 1960 and spent the rest of his life advocating for ocean exploration, for the importance of understanding what lies beneath. He described the descent not as a conquest, but as a visit, a very brief, very humble visit to a world that has no use for us, that managed perfectly well before we arrived and will manage after we leave. James Cameron came back from his 2012 descent and immediately began working on our film, Deep Sea Challenge. That documented the expedition. He described the experience as profoundly isolating, a place so remote, so unlike the world above, that the usual reference points for what space means, what size means, what life means, simply didn't apply. Victor Vesco came back from the five deeps with a sense of how little we know about the ocean and how much the ocean matters for the planet, for the climate, for the chemistry of the atmosphere, for the water cycle that sustains all life on land. He has advocated for ocean science, for the protection of the deep ocean from the mining and the pollution that threatened it. What each of these people brought back was a version of the same thing, a recalibration of scale, a recognition that the world extends far beyond the limits of ordinary human experience, that the surface is the thin skin of something much deeper, the same recalibration that the Amazon gives, that the Ordovician gives, that the exoplanets give. The deep does it in a particular way because the deep is here on this planet, not millions of light years away, not hundreds of millions of years ago, here, now, 11 kilometers below the surface of the Pacific Ocean, and yet as alien as any distant world, as any extinct ecosystem, as far from ordinary experience as anything in the universe that we know about. Part 17, the patience of dark water, what the trench teaches about time. The Mariana Trench has been accumulating sediment since it formed 50 million years ago. The sediment layer at the bottom is perhaps several hundred meters thick. In some places, more in others, depending on the rate of sedimentation over the history of the trench. Each centimeter represents thousands of years of foraminifera dying at the surface and falling through all the zones of the ocean to the floor, where they accumulated and were compressed and became the pale, soft, light-colored sediment that the submersibles disturb when they land. The sediment is un archive, a record of the surface ocean over 50 million years. The species of foraminifera in each layer tell us about the temperature of the surface ocean when they lived and died and fell. The isotopic chemistry of their shells tells us about the carbon cycle, about the oxygen cycle, about the state of the climate at the time they formed. A sediment core from the Mariana Trench is a 50 million year record of the Pacific Ocean's history, layer by layer, year by year, in compressed, pale, beautifully preserved form. Scientists drill these cores with specialized equipment, recover cylinders of sediment, meters long, and read them like books, pages of climate history written in calcium carbonate by organisms that had no idea. They were keeping records. This is what the deep does. It preserves in the stillness, in the cold, in the absence of turbulence and bioturbation, and the disturbances that destroy records in shallower environments. The deep keeps what it receives for a very long time. The sediment remembers everything that fell into it. And in the sediment, now among the foraminifera of the Eocene and the Miocene and the Pliocene and the Pleistocene and the Holocene, there are plastic fibers, microplastic from the last century, a layer in the archive that will be readable by whatever scientists study it in the future, long after us, a thin layer of polymer in 50 million years of biogenic sediment, saying something about the 21st century that we might or might not be proud of. The final drift, letting the depth carry you down, and now the last part, the slow descent, not into the trench, but into the place that sleep takes you, which is also deep, also dark, also full of things you didn't put there, that are simply part of the territory. Let the pressure of the day release the way a bathyscaphe releases its iron ballast. When it is ready to rise, the weight falls away slowly, and the vehicle rises toward the light. But first, before the release, there is the resting on the bottom, the stillness of the deepest point, where the only movement is the slight settling of the disturbed sediment and the slow passage of a sea cucumber across the pale floor rest here for a moment at depth where the pressure is equal on all sides, where there is no up or down in any experienced sense, just pressure, constant from every direction, equalizing the way the body equalizes when it finally, truly lets go. The amphipods are somewhere in the dark, moving on their small legs across the sediment, finding whatever there is to find, patient, without hope or despair, just moving, just searching, just doing the specific thing they evolved to do in this specific place, at this specific depth. The snailfish is somewhere in the water column above the floor, its translucent body invisible in the darkness, its lateral line reading the pressure waves of water moving around food, around other snailfish, around the amphipods. It occasionally eats. The snailfish doesn't know that it is the deepest fish ever recorded. It doesn't know what a record is or what depth means. As a concept, it just swims in the world that is its world. As it has always been, the foraminifera are dying right now at the surface of the Pacific Ocean, above the Challenger Deep, tiny, invisible, their single-celled lives, ending their small calcite shells, beginning the long fall to the floor. That will take perhaps years, drifting through the water column, through every zone, down in the slow, patient, dark. You're breathing slow now, the thoughts settling like sediment in still water, not fighting, not hurrying, just finding their level in long, patient, the way the cold polar water descends from the surface, where it formed down through the water column, taking decades to reach the deep Pacific. One breath of the planet's thermohaline circulation taking a century for one round trip and out, releasing the way the Pacific plate releases heat at the hydrothermal vents along the spreading ridges, slowly, continuously, a geological exhalation that has been happening since the plate was formed 180 million years ago. The Mariana Trench is still there, as it has always been, will be after this night, after every night, moving with the plate, consuming the Pacific floor, centimeter by centimeter, year by year, in the dark, cold, patient, alive, and you are at the surface, in a room somewhere on the land that exists because of the same tectonic processes that created the trench, the same subduction that pulls one plate down, pushes another up, creates the volcanoes that build the islands, that build the continents, that build the land you are on. Right now, the trench pulled down, the land rose up. You are here because of the process that made the deepest point on Earth. You and the snailfish, products of the same planet at different depths, on the same surface of the same world, sleep now. The trench is deep and old and full and patient. Sleep. The amphipods are moving in the dark. Sleep. The foraminifera are falling slowly through the water column toward the floor that has been waiting for 50 million years to receive them. Sleep, the pale sediment, is accumulating layer by layer, year by year, the archive that remembers everything. Sleep, the snailfish, is at the limit of what vertebrate life can endure. 8,336 meters. Below everything, alive, perfectly adapted to its world as you are to yours. Sleep, the Mariana Trench, doesn't need your attention to continue being what it is it never has. Sleep, the deep, is the deep whether you think about it or not, whether anyone thinks about it or not. It simply is the darkness at 10,935 meters, is the same darkness that falls on the other side of your eyelids right now, the same absence of photons, the same complete, total dark, but yours is warmer and the pressure is only 1 bar and there is a ceiling above you and walls beside you and the soft surface you are lying on and the familiar sounds of wherever you are and the body that has carried you through this day, now resting, now releasing, now descending, not to 10,935 meters, just to sleep, just to the depth that the body needs every night, the depth where the day dissolves and the chemistry of the mind does its maintenance, and the atoms that were in stars before the sun was born rest in you for a few hours. In the dark, the trench is patient, the deep is patient, the earth is patient. You can rest. The pale sediment accumulates. Sleep. The amphipods move across the floor of the deepest place on earth, and you sleep in the dark, both of you on the same planet at different depths, both real, both alive, both exactly where you are supposed to be. Sleep.